bond energies in the valence multipole model. So what we are doing with, so we're working with Dr. Bickmore and one of his colleagues, Matthew Wander, for this project. And it's a fairly new project, so we're just in the beginnings of what we're doing. We're just collecting data at this point, and eventually we'll do data analysis.
So this is to get you thinking about why models are important, and they actually do help people.
Really ridiculously good looking? I mean, maybe we should be doing something more meaningful with our lives.
Like helping people. Derek, what people?
I don't know. People who need help.
Models help people. They make them feel good about themselves.
They also show them how to dress cool and wear their hair in interesting ways.
Yeah.
I guess so.
Know what could really help you sort through these important issues?
What? Orange mocha frappuccino?
Okay, so the question that we came across is there more to molecules than them being really, really, really ridiculously tiny and small? And what can models do to help people understand these things? So when it comes to modeling, there are three types for the most part. The first one is like conceptual model, when you take ideas and formulate, I guess, another idea to model the project that you're working on. The second type of model that we're dealing with is a physical model. For example, we have stream tables where you can see actual movement, make predictions, and run calculations on what you see. But both the conceptual model and the physical model lead to a mathematical model, which is used to predict, make calculations on what we see. Mathematical models are important. They're definitely a lot cheaper, a lot quicker to make calculations, to make predictions, and can help us see beyond the scope of what we're looking at.
And so the model we're trying to develop is one that will help us understand molecules and how their energies within the bonds affect their shapes and their reaction rates and things like that.
Yeah, so we're primarily dealing with diatomic molecules, so any two elements we'll take and see how they interact with each other. So the point we're at right now with our research is using a mathematical model to predict bond energies, dipole moments, and bond lengths between just any two elements we find on the periodic table. The reason that we are doing this is because, like a periodic table, we have specific trends within elements. We want to create overall a diatomic periodic table, like help predict trends within like the interaction of two elements.
And so the basis for our model is going to be bond association energies. If you remember from chemistry, these energies are stored within the bonds and are either released or put in during a chemical reaction. So here we have an example, H3C bonded with H, so that's CH4 methane, and it's breaking up to form CH3 and hydrogen. And so in this instance, the energy could be represented by that exothermic reaction, the energy coming off of the bond. And the bond energies help us predict not only the structure of the molecule, but also the reaction energy, the reaction rates, and things like that. So there have currently been studies to find the bond association energies of some diatomics, but those studies are incomplete, and there's frankly not enough information to create a solid mathematical model.
Yeah, so this is an example Dr. Bickmore and some of his students created a few years ago, or I think it was last year. And it's somewhere around like 40 different diatomic molecules. And they were able to predict, we have here our bond energy, and then we have your ionicity, and then you have your bond valency. And so what this is showing is that, so we have like an increasing ionicity, which is, I don't know if you guys remember from chemistry, but when it comes to ionicity, you have like covalent, metallic, and your ionic bonds where electrons sort of gravitate more towards one element rather than the other. And so with their model, they were able to see that an increase of bond energy, you increase the ionicity. But this was only for the 40 diatomic molecules. There are over 10,000 that we are trying to do calculations for. So far we've done about 2,000 calculations and we still have 800 or 8,000 more. And on top of that, we're going to rerun it to do a different type of calculation. So at this point, or if you want to go back a slide, what we are looking at is the bond energy at its lowest state. So we will see like you have your two atoms, your two elements, and the bond energy at its lowest state. So we don't understand too much of what's going on just because it's like new to us and a pretty new research, but we have our bond energies and then we calculate the length between them and the dipole moment.
And so this is just another way to look at the data. Here we have bond valency on the x-axis and bond energy on the y-axis. And this is our predictive model based on bond valency, which is just information you can get from the periodic table. And right now the current model they have is accurate to within about 200 kilojoules. And so it's good for noticing general trends, but not for making specific calculations. And so that's why we're running all these other diatomics, 10,000. It's every possible combination of two elements in the periodic table. And so these are calculations that we run on a supercomputer, and they optimize the geometry of the molecules so that we can find out the bond length at different spin states as well as the dipole moment. And all this data will have to be run through again. So right now we're doing the geometry optimization, but then the next step in our research is to do a scan of the diatomics and see as we pull them apart how the energy in that bond changes with length. And so this is a Morse diagram that shows the bond distance on the x-axis and then the energy on the y-axis. And so you can see there's this little trough that it creates as the bonds get farther and farther away. The energy reaches closer to zero. And so the bond dissociation energy that we're going to try to find from all this is the distance from the zero line to the bottom of the trough. And with that bond dissociation energy, we're hoping to make the model that'll help us complete what's already been started.
Yeah, so this is just an example of a periodic table. Let's see, the University of Utah created. I think there are only a handful of these models out there. This is just part C, so we're looking at just transition metals. And as you can see, there's a lot of data that we don't have for these type of diatomic molecules. So they have a general idea of what's going on, but we just want to solidify the research and make a concrete periodic table to show trends and different things going on. Like we said, we're starting this project. We started it just a couple months ago, trying to calculate all of the data. It takes about 8 hours to run one diatomic molecule using the Fulton supercomputer lab. And so we're running into a lot of errors, and we're trying to fix those things. And once we complete all 10,000 of the optimization, we have to run it again. So yeah, that's where we are with our research at this point.
Yeah, and once we do have this complete periodic table with all this extra data, it's something that can be used by chemists, geochemists. It'll just be a good data source for a bunch of different disciplines, and it will help people.
Have you found any trends so far in the research that you've done?
We're still in data collection, so we haven't started our analysis yet. But they did the similar thing in the previous study when they were able to notice these general trends. So it's clear that there is a trend. There's just only 40 diatomics being studied at this point. So we just want to flesh it out with the rest of the data.
Is your research, is it an expensive thing to do, or is it all just done on
Like, I'm just curious, like, your methods a little bit, like how the research is actually.
So it was actually Dr. Bickmore and Matthew Wander that came up with the calculations, and then they write a script that we submit to the supercomputer, and then what Bonnie and I are doing is we just take the data from the completed script and just input it into a workbook in Excel. So when it comes to the mathematics, it's really complicated, according to what Dr. Bickmore and Dr. Wander have told us. They haven't really shared exactly what the formula is for these calculations, but if you think about it, it takes a supercomputer 8 hours just to do an optimization of 2 elements.
And we're competing with a lot of other people on campus who want to run jobs on the supercomputer, so it's more time intensive than anything.
Yeah.
It looks like the list of your elements that you're working on so far, is that the list of yours?
On the
Might be the next one. Yeah, this one here.
Yes.
So, okay, so they're also metals, I don't know if they're transition metals, but are you also working on that same table?
Yes, yeah, we're doing like transition metals, we're doing metals, we're doing just all of them. So your noble gases.
Yeah,
which
there's a
we
lot
know more about.
of other tables like this for the other different types of elements. They just separate it because otherwise the table just gets too big. It's hard to visualize.
Yeah, so I think like the part B is your metals, and then part A was I think like noble gases or non-metals, yeah. So yeah, there's the tables, they're just really large.
So you're just doing a whole variety at this point, you're not necessarily targeting.
Yeah, we're having trouble with landides and yeah.
They're just really large. It takes a lot.
Yeah.